Calculus video 48, an example of concavity and inflection points. So we're going to determine the following: the intervals on which the function is concave up and concave down, and the inflection points, the points at which the curve changes concavity. And we're going to use our old friend f of x is equal to x squared times the square root of x plus 1 on the interval from -1 to 3. We've already done a lot of work with this. We've kind of curve sketched it already. We have the absolute extrema, the relative extrema, the increasing, decreasing, the y-intercept, all that stuff. So we've found in a previous video, I believe that was video 46, if I'm not mistaken. We found all that other stuff, including the derivative. But I'll go ahead and find the derivative again. The first derivative, actually, let me rewrite this. The original function as x squared times x plus 1 to the 1/2. The first derivative, if you remember, was 2x times x plus 1 to the 1/2 plus x squared times, bring the 1/2 down, x plus 1 to the -1/2 times 1. And we said if we ever have one of these exponents where it's like a negative exponent, we often, more times than not, want to multiply top and bottom by the positive version of that exponent. So we're going to write this over 1, and we're going to multiply this whole thing by x plus 1 to the positive 1/2 over x plus 1 to the positive 1/2, distributing that here and here. That gives me 2x times x plus 1 plus 1/2 x squared over x plus 1 to the 1/2. That's 2x squared plus 2x plus 1/2 x squared over x plus 1 to the 1/2. That is 2.5x squared plus 2x over x plus 1 to the 1/2. Right, so we found first derivative. Here is f prime of x. Okay. In order to find concavity and inflection points, we need to find the second derivative. So it's the derivative of the first derivative. We are going to take the derivative of 2.5x squared plus 2x over x plus 1 to the 1/2. It's a little messy, but hopefully in the end it won't be too bad. Looks like a quotient rule to me. So I'm just going to rewrite it here. F prime of x is 2.5x squared plus 2x over x plus 1 to the 1/2. Therefore, f double prime of x, quotient rule, is derivative of the top, 5x plus 2, leave the bottom, minus, leave the top, 2.5 x squared plus 2x. I probably did not give myself enough room. I need some more room here. Let's try that again. F double prime of x is equal to derivative of the top, 5x plus 2, leave the bottom, x plus 1 to the 1/2, minus, leave the top, 2.5x squared plus 2x, derivative of the bottom. So that's going to be a chain rule. We're going to bring the 1/2 down. We'll have x plus 1 now to the -1/2 times the derivative of the inside, which is just 1, all divided by x plus 1 to the 1/2 squared, which is just x plus 1. Okay, once again, I've taken the derivative, and I end up with this x plus 1 to the 1/2 and x plus 1 to the -1/2. We're going to follow the same idea. We have an x plus 1 to the -1/2. I don't like that. Therefore, I'm going to multiply top and bottom by x plus 1 to the positive version of that to the positive 1/2. Again, that gets distributed here, and it gets distributed here. And again, the reason is when I multiply the x plus 1 to the 1/2 times this x plus 1 to the -1/2, it's the same base. You add the exponents, you get 0, and that part goes away. Also, it helps out because x plus 1 to the 1/2 and over here times x plus 1 to the 1/2 is just x plus 1. So we get a lot of simplification from this. We get 5x plus 2 times x plus 1 to the 1/2 times x plus 1 to the 1/2, or just x plus 1. Minus, I'll bring this 1/2 out front here, 2.5x squared plus 2x. And then the x plus 1 to the negative 1/2, x plus 1 to the 1/2 cancel, so that part's done. Over x plus 1 now to the 3/2. Right, because this is x plus 1 to the first, and that's x plus 1 to the 1/2, and you add 1 and 1/2, and you get 3/2. Okay, let's simplify. Again, remember we're trying to find when is the the second derivative equal to 0, and when is the second derivative undefined. So a little bit of simplification. I'll distribute the 5x plus 2 times the x plus 1 and get 5x squared plus 5x plus 2x plus 2. Minus, distribute that negative 1/2, 2.5, 5 over 2, so let's, what we call it, 5 over 4, or 1.25x squared, minus x, 1/2 times 2, 1. 1/2 times 2 is 1, over x plus 1 to the 3/2. Okay, so that would be 3.75x squared plus 5x plus 2x is 7x, minus x is 6x, and then plus 2. Okay. There you go. There is our second derivative. Well, we need to find out when this second derivative is equal to 0 and when it's undefined. So second derivative equal to 0, that's going to occur when the numerator is equal to 0. And second derivative undefined is going to occur when the denominator is equal to 0. But let's take care of this part first. You could, right now, try to factor it or do the quadratic formula. It'd be fine. Quadratic formula here, great. I don't really like the 3.75 in there, although it's not bad. I might consider multiplying everything times 4 to get rid of the decimal. All right, I might do like 3.75 times 4 is 15, and then everything else times 4. I might call this 15x squared plus 24x plus 8 equals 0. All right, 0 times 4 is 0 still. So just multiplying both sides by 4. Just to get rid of the decimal, but you don't have to do that. And then I don't know if this factors or not. Multiplies to 120, adds to 24. I'm not seeing it, so let's just go with the quadratic formula. Alright, so we get x is equal to, my a value is 15, my b is 24, my c is 8, and I get quadratic formula, x is equal to negative b over 2a plus or minus the square root of b squared minus 4ac over 2a. Alright, so negative 24 over 30, those both divide by 6. That's negative 4/5 there. Plus or minus square root of 24 squared minus 4 times 15 times 8 is 96 over 30. Now 96 divides, I believe, by 16, yeah. So I can rewrite this as x equals negative 4/5 plus or minus square root of 16 times square root of 6. 16 times 6, 96 over 30. That is equal to negative 4/5 plus or minus 4 root 6 over 30. 4 and 30 divide by 2, so negative 4/5 plus or minus 2 root 6 over 15. Alright, what I found is, I have found the values of x such that the second derivative is equal to 0. These are my would-be critical points, but we're in the second derivative here, right? So these are kind of like possible inflection points, we might call them. Possible inflection points. They'll be inflection points if the slope changes sign, if the concavity changes changes sign at those points. If it goes from concave up to concave down, or concave down to concave up. Now, I like the exactness of this answer, but really a decimal would work just fine here. So I'm going to go ahead and get a decimal out of this. And I'm getting an x value equal to negative 0.47 when I think I did the addition there. And then also an x value of negative 1.13. Good, okay. So x is negative 0.47, x negative 1.13. Those are possible inflection points. Possible inflection points. So once I have those, what we're going to do is take that number line idea, this time with the second derivative. Remembering that we're only going from negative 1 to 3. If you remember from the problem, from way up here, we're only speaking about this problem on the interval from negative 1 to 3, so that's all I'm going to care about. And we see that if we're only going from negative 1 to 3, negative 1.13 is over here, which means that's not part of our domain. So it really can't be an inflection point, so crossing that one out, our only option now is the negative 0.47. So what we're going to do is we're going to pick test points. We're going to pick a test point between negative 1 and negative 0.47, maybe like negative 0.5, barely to the left of that, but it'll work. And between negative 0.47 and 3, I like 0, any option. Anytime I can, I'll take a 0. And we're going to plug those into the second derivative. And let's remember that the second derivative is, oh, I forgot something. Well, I'll come back to that. Is this thing here for the second derivative. It's this. What did I forget? I forgot to check for when the second derivative is undefined. Let me back up. When is the second derivative undefined? That occurs whenever the denominator is equal to 0. That makes it divide by 0. That's undefined. That occurs when x plus 1 to the 3 halves is equal to 0. Multiplying or taking each side to the power of 2/3, we get that x plus 1 is 0. We get that x equals negative 1, which happens to be an endpoint. So we won't change concavity at negative 1 because we don't have anything to the left of it to change from, so we won't consider that to be an inflection point. Okay, so none there. The only thing we have to check is the negative 0.47, and so we're going to do our endpoints here, negative 0.5 and 0, looking into the second derivative of negative 0.5 and the second derivative of 0 to see whether they are positive or negative. Positive being concave up, negative being concave down. Okay, I again have forgotten what the second derivative was. 3.75x squared plus 6x plus 2. F double prime of x, 3.75x squared plus 6x plus 2 divided by x plus 1 to the 3 halves, I believe. Okay, very good. Once again, the denominator is going to be positive. Anything here with the 3 halves, that's like saying you're cubing it and then square rooting it. Because it's the square root of something, it's got to be positive. So the denominator is going to be positive. So we just need to really check the numerator. And when I plug in 0, like the easy one first, my numerator is 2. Therefore, 2 divided by something positive is something positive. And so I'm getting positive here, concave up. And negative 0.5, let's go ahead and check that out. So 0.5, negative 0.5 squared times 3.75 plus 6 times 0.5 negative plus 2, negative 0.0625. Okay, point is it's negative. Therefore, negative. So it is concave down from negative 1 to negative 0.47, concave up from 0.47 to 3. Concave down, again, parentheses, not brackets here. Concave down from negative 1 to negative 0.47, concave up from negative 0.47 to 3. Because it switched concavity, it went from concave down to concave up. That means that negative 0.47 is an inflection point. So we get an inflection point at negative 0.47, comma, guess what we're going to need? A y value. We need a y value here. So we got to go all the way back to the original function, f of x equals x squared, square root of x plus 1. And ask ourselves, what is f of negative 0.47 to get the y value? I'm getting 0.16, somewhere around there. And so we have an inflection point at negative 0.47, 0.16. Okay. Does that fit with what we had as a graph from the previous curve that we found the other information on? Let's see. If you remember this curve, we have this. We had a point at 0, 0. We had a point over here at negative 1, 0. At negative 0.8, I can't remember the y value, but it was somewhere about right there. And then at 3, I believe it was all the way up at 18. And so we had a curve that looked kind of like this, and then kind of like that. Oops, no arrow, just point. Okay. So from last time we had a relative max here, we had a relative min here at 0, 0. The question is the concavity right here? Yeah, I think so. If we do negative 0.47, it's kind of about right here. It's kind of that point as our inflection point, IP. We see that, yeah, that makes sense. From negative 1 to negative 0.47, that looks concave down to me. I'd believe that. And to the right of that, from negative 0.47 all the way to 3, probably a poor drawing. It kind of flattens out more than it maybe should. But yeah, that looks like that would be concave up. So we could put in here, we're concave down here. And concave up over here. Very good.